two of the most fundamental scheduling policies for real-time systems are rate-monotonic scheduling, or RMS, and earliest deadline first, or EDF. We'll first look at rate-monotonic scheduling, which is a static priority system. The priorities of processes don't change during execution. RMS uses two parameters for processes. Ti is the computation time of process I, and tau I is the period of process I. The RMS model makes several assumptions. All processes run on a single CPU. Context switching takes 0 time. Process execution time is constant. The activation time for every process is at the beginning of its period, and the deadline is at the end of the period. And the scheduling rule is that the highest priority ready process runs. Now note that this makes no assumptions about the relationships between periods. So for example, in a simple example, you can have P1 with these periods, P2 with this period, P3 with a very different period, and P4 with yet another period. Rate monotonic analysis allows us to determine what priorities should be assigned to the different processes. It assumes static priorities. Response time refers to the time required to finish a process, including all the interference from other processes. And in rate monotonic analysis, the critical instant is the state of the schedule that gives the absolute worst response time for a process. And that always happens when all the higher priority processes are just ready to execute. So in this case, P4 is ready to execute, but so are P1, P2, and P3. We have to make sure they all execute before P1. We have to make sure they can all execute before P2. We have to make sure they all execute before P4 can finish. But P1, P2, and P3 don't just execute once. They'll execute several times before P4 can finish. This analysis leads us to an interesting result. The optimal way to assign fixed priorities to processes is based on period. The process with the shortest period gets the highest priority. The next shortest period gets the next highest priority, and so forth. So priority is inversely proportional to period. If we have ties to processes that have the same period, we can break ties arbitrarily. So notice that this rule doesn't depend upon the computation times of the tasks, only the periods, and no fixed priority scheme does better. Let's think for a minute about the utilization of RMS. For arbitrary deadlines, the critical instant doesn't always happen. Remember that the critical instant happens when all the processes line up and are just ready to run. That happens occasionally, but not all the time. So the schedule has to be designed to account for this worst case. But when this worst case doesn't happen, the CPU has idle CPU time that's only used during the critical instant. Now, of course, some combinations of deadlines can allow for 100% utilization, but RMS in general doesn't guarantee 100% utilization of the CPU. We can understand this a little better with an asymptotic analysis to see what happens when we increase the number of processes. So the utilization is the sum of the ratios of the computation time and the periods. As we increase the number of processes to infinity, with no restriction on the relative periods, you can prove that the maximum utilization approaches 69%. So remember that for particular combinations of periods, we can get 100% utilization. But this asymptotic result illustrates the fact that RMS doesn't always use 100% of the CPU. It does, however, guarantee that it meets its deadlines. In contrast to RMS, earliest deadline first dynamically changes the priorities of processes during execution. The priorities of processes in EDF are determined by their distance to the deadline. The task closest to its deadline has the highest priority. so the priority of a task changes during execution. This timeline shows the deadlines of processes. So at this point in the schedule, P1 is closest to its deadline, so it has the highest priority. At this point, P2 is closest to its deadline, so it would have the highest priority. And at this point, P3 is closest to its deadline, so it has the highest priority. We can show that EDF is able to schedule all of its tasks if the utilization is less than or equal to 100%. Of course, if the CPU is overloaded, the failure analysis for EDF is more complicated because the priorities of the tasks change. Let's compare RMS and EDF. RMS is easier to understand and it requires a little less scheduling overhead, but EDF can schedule some tasks that RMS cannot. This example illustrates a set of processes that EDF can schedule that RMS cannot. The colored boxes show the locations of the deadlines of the different processes. And at the bottom, we have lines for the RMS schedule and for the EDF schedule. So this example has 3 processes. P1 has a computation time of 1 and a period of 3. P2 has a computation time of 2 and a period of 4. P3 has a computation time of 1 and a period of 6. We can see the critical part of the schedule right here. At time 5, RMS schedules P2 because that has the highest priority in a static priority system. However, EDF schedules P3 because P3 is closest to its deadline at T6 here. So that allows P3 to finish. This graph doesn't show the RMS schedule past time 6 because at that point, RMS has missed the deadline for P3. To summarize, rate-monotonic scheduling is a static priority scheduling policy. Earliest deadline first uses dynamic priorities. Each has its advantages and disadvantages, but both can be analyzed to determine when they guarantee that a set of processes will meet all their deadlines.